Okay. So first of all, on your notes, it says transformations of square root functions. The new part today is cube root. We are looking at cube root right now. Okay, and his name is not Curtis. It is Curly. Not that that matters. Okay, and so to look at what our parent function looks like, we're just going to plug in some x values. If I plug in -8, the cube root of -8 is -2. So for cube root, we're actually allowed to plug in negatives this time, because if I cube -2, I can get negative values, which would be -8 in this case. And so then the cube root of -1 is -1. The cube root of 0 is 0. Cube root of 1 is +1. Cube root of 8 is 2. Okay, so when I plug in these points, we still have 0, 0, and 1, 1 on our graph. But then we have 8, 2. And so this function goes up to the right, kind of like square root does. But now we have these other points on the other side. We have -1, 1, and -8, -2. So it's kind of like we have two square roots, one in the normal position and then one like reflected on the other side. Okay, and so where we have that change in concavity, we talked about this with the cubic parent function. That's called an inflection point, where it changes direction. And so that's at 0, 0 for our parent function. Okay, and so this is also the point of symmetry, because he has rotational symmetry. If I rotate him about the inflection point, he will look exactly the same. Looks exactly the same. Okay, and so this is the inflection point, but it is also the point of symmetry. So if a test question asks for either of those things, they're asking for the exact same thing. And for the parent function, it's 0, 0, but of course we're going to move left, right, up, down, and so we'll have to keep track of that. So rotational about 0, 0. Oh, I'm not on the screen. Rotational. We're back to rotational symmetry, just like the rational parent function, just like the cubic parent function. And so here, his x-intercept and y-intercept, where he crosses the axis, is 0, 0. But of course, that's going to change as we move this function left, right, up, and down. And so we'll look at some examples of how to find it if it's moved. And then cubic and cube root have the easiest domain and range. Both of them are all real numbers all the time. You don't care what kind of ugly transformations you put on this graph, it's still going to be an S shape that goes to all real numbers in both directions. So all real numbers all the time. And so if we're not given an interval to look at, there's no max or min, because it's going up forever, down forever, off to positive and negative infinity. So D and E for both, unless they give you an interval. And we'll look at how to find those on an interval on the back. Okay, and so let's talk about how to graph these using the pattern. Okay, and so on the front here, I'm going to graph the cubic parent function that we looked at first semester. 2 cubed was 8. And so remember, the cubic parent function, x cubed, made that tall, skinny s, whereas the cube root is like a short, fat s. Okay, so they both have that linear relationship by the inflection point. just all the x's and y's are switched for the inverse function. So that's why it looks like that. Okay, and so to graph this, we're going to look at the pattern. Remember, let me get another color. Remember, if there's no Rx or Ry, you should have an increasing function. Okay, increasing function. Y'all remember talking about that last semester? And so if there's an Rx or Ry, it looks identical because of the symmetry, you will have a decreasing linear relationship between those 3 points. And so if there's a reflection of some sort, that's how we're going to graph it. We're going to graph it as a decreasing slope rather than an increasing slope. Okay, the other thing we need to remember about the relationship between the points is that for the x's, we're going over 1 and then up 1 to get to our next nice point, and then over 1, up 7. So the change in x here was 1, 1, over 1, whereas, I'm going to put a comma between those, whereas the change in y was 1, then 7. Y'all remember that 1, 7 pattern? And so for the cube root parent function, it's going up 1 over 1, up 1 over 7. So that is switched. This time your 1, 7 pattern happens in the x direction, whereas your 1, 1 pattern happens in the y direction. Okay, and so let's start with B, and then we'll go back to square root and look at his pattern in a second. Okay, so the first thing we're going to do is just list the transformations. And so first we have an Rx. Second, we have a vertical stretch by 3. And be careful not to confuse the index of your radical with a transformation. That index of 3 just tells you you're dealing with cube root. This big 3 out front, that's your actual scale factor. So your index is not a transformation. That's just your function. Okay, so vertical stretch by 3, and then we have our right 2 down 4. Okay, and so when we're trying to graph this with 3 good points, remember we always start with the significant point. So start with the inflection point. And then we determine the direction. And then lastly, we deal with stretches and compressions, our scale factors. Okay, and so here, our inflection point has been moved right 2 down 4, right 2 down 4, right 2 down 4. So at least get your inflection point in the right place. Okay, the direction, because of this Rx, he is no longer increasing, he is decreasing. So when we get our good points, we have to make sure we're graphing it as a negative slope, not a positive slope for those 3 points. Okay, and then lastly, we take care of the scale factor. And so we had a vertical stretch by, oh, that is not an S, vertical stretch by 3. And so our original change in X, change in Y, we said was 1, 7, 1, 1. This vertical means we are changing this by a scale factor of 3. So we're going to keep that 1, 7 pattern in the X's. If it was horizontally stretched or compressed, we would be changing the X's. Okay, so from this point, we are going to go up 3, back 1, up 3, back 7. 1, 2, 3, 4, 5, 6. There we go. Okay, I'm going backwards because of the decreasing direction. I need a negative slope. So up to the left. Remember, treat it kind of like square root, and then we'll get the other part over here. Down 3 over 1, down 3 over 7. Barely makes it on the graph. So now treat it like an upside down square root connected at the inflection point. Okay, so that's what your vertically stretched cube root function looks like. He's tall, so he looks kind of weird. It's vertically stretched, he's taller. Our change in y's are now 3. Okay. So now we do the same thing with square root, only now remember we're not dealing with an S shape. We're back to our square root function. And so I'm going to put him right here. He had the points 1, 1, 0, 0, 1, 1, and then 4, 2, and 9, 3. And so he looked like that. Okay, and so the starting point is 0, 0, and then if we're looking at the pattern, he goes up 1 over 1, up 1 over 3, up 1 over 5. So we have a 1, 3, 5 pattern just like we did for quadratics, only now the 1, 3, 5 pattern is our change in x. Okay, the change in x's go from 1 to 3 to 5, but the change in y's are just up 1 every time. For these inverse functions, our change in y's are the ones that stay consistent. Okay, so we're going to use that to help us graph this square root function. So you are going to be going back and forth from square root to cube root on your radicals test, and so you really got to keep straight. Like, what am I dealing with, an S, or am I dealing with Squidward, the square root? Okay, so let's list our transformations, and in fact, they're all the same. We have our Rx, our vertical stretch by 3, a right 2, down 4. Okay, and so when we're sketching this, we don't call that an inflection point, obviously, because it's not an inflection point. We're calling it the starting point. And then we'll determine the direction. And then take care of the scale factor. Okay, and so the original starting point is 0, 0, but we've moved right 2 down 4. Right 2 down 4. So there's our new starting point. Okay, and then the direction, that Rx takes our parent function and flips him upside down. So he is down to the right. Okay. And then our scale factor is another vertical stretch by 3. And so our change in x, which was 1, 3, 5. Change in y is 1, 1, 1. Our 1, 3, 5 pattern is going to stay the same. We have not horizontally stretched it. We have vertically stretched it. And so vertical tells me I'm changing the y's by a scale factor of 3. Okay, so be careful. We're going down into the right because of the reflection. And so I'm going to go down 3 over 1, down 3 over 3, and then if I had more room, I would go down 3 over 5, but I'm out of room, so they just said 3 good points, we're done. And so we know it would continue off our graph. So anytime they're vertically stretched, they look weird. You can just imagine like stretching it out. Okay, so that's how you would graph these. Of course, you're not going to be graphing on your test, but if I give you a graph and ask you to identify transformations, I want you to be able to look at the pattern of the points to determine, hey, there was no stretch or compression here because it's still the same pattern as the parent, or hey, there was a vertical stretch by 3, that kind of thing. So being able to look at the relationship between the points to determine whether or not there was a stretch or compression happening. Right? So now here are some more sample test questions. We're going to talk about how to find x and y intercept for our cube root functions and max and min on the intervals. Okay, and so transformations, inflection point, domain, and range, those are the easy parts. And so let's do those first. Anytime you realize that you are dealing with cube root, you see that 3, that tiny little 3 in the index, don't even look at what the transformations are. You do not care. The domain and range is all real numbers all the time. I always feel like it's a trick question when you ask for domain and range of a cube root or cubic function. I could put the ugliest transformations on there, like plus pi, plus 1,000, plus whatever. You don't care. It's all real numbers all the time. Okay, and so if the question asks you to list the transformations, list them in order, starting with this vertical compression by 1/3, and then right 7, up 6. And so right 7, up 6 puts our inflection point at 7, 6. Here, the only thing under this cube root is the x. So all of these transformations are happening outside the function. So we have an Rx. We have a vertical stretch by 4. Anytime the scale factor is smaller than 1, you use C. Anytime it's bigger than 1, you're using S for vertical. And then we haven't been moved right or left because there's nothing happening to x. It is outside, so down 7. So our inflection point is still at 0 for our x coordinate, but it has been moved down 7. All right, so this next one, this -2 is under the radical with x. So we know we need to put this in good form. Okay, so I need to take this 2 and divide it by 1/2. Dividing by 1/2 is not the same thing as dividing by 2. So be careful. Don't multiply it by 1/2. Divide it by 1/2, which would cause it to be a 4. So negative cube root 1/2 x minus 4. Dividing by 1/2 is the same as multiplying by 2. Okay, and so we have an Rx still because the negative is outside the radical. And then that 1/2 inside is a horizontal stretch by 2. Everything inside the function is backwards and crazy. And then -4 moves you right 4. And so right 4, and then it hasn't been moved up or down, so it's still sitting at 0 for the y coordinate. Okay, so that's how you would deal with transformations, inflection points, and domain and range, and also point of symmetry. So next, let's talk about x and y intercepts. We've been doing x and y intercepts. It's the same. No matter which function you have, if you're looking for the x-intercept, plug in 0 for y. If you're looking for the y-intercept, plug in 0 for x. So let's use blue and red. Okay, so let's start with the y-intercept because that's always the easier one. And so for the y-intercept, your x value is 0. And so for our function, we would have 1/3 cube root of 0 minus 7 and then a plus 6 outside the radical. So that gives us a -7 under the cube root. And so if this was square root, I would stop and say D and E. We can't have square roots of negatives, but we can have cube roots of negative. Okay, and so this -7 is not a perfect cube. If it was like -8, I would keep going and saying, hey, that simplifies to -2 and number crunch some more. If it's not a perfect cube, we can't simplify. can't simplify. So if you run into that situation, that means you're going to have to leave your answer in terms of cube root because you're not going to have a calculator and we don't want decimal approximations. Okay, and so for your y-intercept, in writing, you would have 1/3 cube root of -7 plus 6. That's as pretty as it gets. If you were typing this, type fractions in parentheses, 1/3. Cube root is CBRT. Just like square root is SQRT, cube root is CBRT. That's a programming language. And then in parentheses, we would have a -7. Outside the parentheses, the +6. So everywhere you see that cube root, you're going to have CBRT. And of course, I'll remind you of that in the directions of your test. Okay, and we're not going to do the ordered pair because why make this even uglier? All right, let's see if the x-intercept worked out nicer. Oh, I think this is the one that turns out to be a huge number. You won't have to do huge numbers. Know your perfect cubes up to 8, which you already know from the polynomials unit. But I think this one ends up being huge. Okay, so plug in 0 for y, and we're going to have to solve for this x. Okay, so to get to this x, we have to take care of everything outside the function first. Don't break anyone out of this prison. Treat this radical like a prison. Nobody goes in, nobody goes out. So the first thing we have to take care of is this 6 by subtracting it. Okay, so if I subtract 6 from 0, I get -6 equals the 1/3 cube root x minus 7. Make sure your index stays nice and small so you don't accidentally think it's a scale factor. You don't want to accidentally divide by 3. Okay. The next number we have to take care of is this 1/3 sitting outside the radical. To get rid of a 1/3, just multiply by 3. That's how you get rid of a fraction. So if I multiply by 3, I have a -18 on the left. Cube root x minus 7. Okay, so now if I'm trying to undo a cube root, I would cube both sides. And so this is where I don't expect you to know that what -18 cubed is. So I'm going to leave it like that and type it in my calculator at the end. Okay, and so this cube root and cube cancel out, leaving me with the x minus 7 that is now free. We couldn't do anything with this -7 until this step right now because he was trapped. Now we can add 7 to both sides. And so our x-intercept is -18 cubed plus 7. If you get stuck on a test, leave your answer like that, you'll get a majority of the points. Where's my calculator? Let's figure out what that number is. -18 cubed plus 7. -5,825. Not too bad, but still. Okay, so that's how we find x and y intercepts. There's more x and y intercept questions for example 5 and 6. So let's just keep going with x and y intercepts and we'll come back to these max and min problems. Okay, so starting with the y-intercept, we plug in 0 for x. So that gives me cube root of 0 plus 4. And then a -3 outside the radical. Cube root, 0 plus 4 is just 4. And then when I get to this step, I look and I ask myself, is 4 a perfect cube? It's not. So can't simplify. And so that tells us our answer is going to be left in terms of a cube root. So cube root of 4 minus 3 is our final answer. Cube root, CBRT, of 4 minus 3. That's how you would type it for the y-intercept. Okay, x-intercept, we have to solve an equation. I think I'll go over here. X-intercept. This time we plug in 0 for the output, the y, and solve for the x. Okay, this minus 3 is outside the radical. We have to take care of that first by adding it. Now don't break this 4 out of prison. We're ready to take care of the cube root by cubing both sides. And this one's nice. 3 cubed is 27. Not 9. 3 times 3 times 3 is 27. Last step, subtract 4. And you get 23. Okay, so 23 comma 0. We'll just ask for the value in this case. So 23 for our x-intercept. Love that. Sometimes you get a nice number, sometimes you do not. All right. Example 6, starting with the y-int. X is 0. So that gives me the cube root, negative parenthesis, 0 minus 3 parenthesis, and then a plus 4 outside the radical. That was unnecessarily large. Make sure he doesn't get trapped under the radical. Okay, and so that ends up being cube root of negative 3 under the radical. And we know negative 3 is just 3. And so now, before I go any further, I ask myself, is 3 a perfect cube? It is not. Can't simplify. That tells me my answer is going to have a CBRT in it. Okay, so in writing, we would have cube root of 3 and then a plus 4 outside the radical. Online, we would have CBRT, 3, close those parentheses, and then add the 4. All right, x int. Plug in 0 for the y, solve for the x. That plus 4 is outside the radical. We take care of that first by subtracting it. Now everything left on this right-hand side is trapped under this cube root. This is where we cube both sides. And this one works out nice too. We know negative 4 cubed is negative 64. That's one you would be expected to know. And so now our negative x minus 3 is free. And rather than distributing the negative, go ahead and just divide both sides by the negative, which is technically dividing by negative 1. It would cancel with this negative over here. And so positive x minus 3 equals positive 64. And then when we add 3 to both sides, 67. Oh, it's not an equation. It's technically an ordered pair, but we're just going to type in the value. Don't type in x equals. All right, so that's x and y intercept. Same rule for any function we do. Now let's do the max and min. This is where you need your picture, but honestly, for cube root is so much easier than square root because you don't run into a D&E situation. We have this big S that extends everywhere. No matter what interval I give you, it's going to exist. and the max and min is going to exist at one of the endpoints. You don't worry about asymptotes, starting points. This one's nice. Okay, but you still want to sketch it so that you know which one is your max and which one's your min, and you'll see why. It's really hard to tell which number is bigger just by looking at the number because they're not pretty numbers. So let's start with example 3. They gave me the interval 2 to 6. And so I know I'm going to have to go 2 to 6. And then this function has an inflection point at 0, -7. So when I make my axes, I want to make sure it goes down to -7, but also includes that 2 and the 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay. And so remember, this interval, these are x values. And so we're only allowed to look between 2 and 6, between these green lines. And then our function has the inflection point at 0, -7. And he's been reflected, so we know he's decreasing. So he's going up to the left, down to the right. Okay. That's important because now I know it is decreasing as I go to the right. And so if I'm trying to find the max and min, this y value is going to be higher than this y value, very subtly, because it's decreasing so slowly. And so this is clearly higher than this. And so if the question is asking for the maximum, I want this one. This y value is higher. And then if the question is asking for the minimum, I want this value. It's so subtle because they're so close in value. And that's why you really want the picture. Okay. And so starting with the maximum, I know I'm going to be plugging in the 2. I'm going to do the max in red. Okay. So x equals 2. Let's grab our rule, which is negative square root. Oh, not square root, cube root, sorry. Tiny little 3. Negative cube root of x, which we know is 2, and then a -7 outside. Okay, negative cube root of 2 minus 7. Now I ask myself, is 2 a perfect cube? No. So we can't simplify. So our answer has a CBRT. Negative cube root of 2 minus 7. Sometimes it's nice because you don't have to number crunch. The only pain is you have to type all that. Okay, so that's our max. Let's do the min. Circle it in blue and point over here. So for the min, we're plugging in 6, the other endpoint, which gives us negative, oh, I missed the 4. Don't let me miss the 4. There's a negative 4 in front of the cube root, so just put a 4 right in front of your CBRT, negative 4 cube root of 2. Okay, so negative 4 cube root of 6, and then a -7. Now I ask myself, is 6 a perfect cube? Nope. So that's as pretty as it gets. Negative 4 cube root of 6 minus 7 outside the parentheses. And that's exactly how you would type it. No spaces, no weird symbols, no extra parentheses other than around the 6. Okay, this last one, my interval is going from 0 to 8. And it's also been moved right 4. So 1, 2, 3, 4, 5, 6, 7, 8. It's been moved right 4. Well, let's go ahead and graph the interval. So our interval this time is 0 to 8. And then our inflection point is at 4, 0. And because he's been reflected, he is decreasing. So make him look like square root up to the left. And then connect the other piece. All right, so this one's a little more obvious which one's your max and which one's your min. Obviously, this y value is higher than this y value down here. But you'll see when we plug these numbers in, these do not look pretty. Okay, starting with the max, let's do that in red. So for the max, we're plugging in 0, the left endpoint. That gives me negative cube root, and then let's just use this form because I messed that one up. 1/2 of 0 minus 4, which is negative 4. Okay, and then 1/2 of negative 4 is negative 2, so I have negative cube root of negative 2. Negative 2 is not a perfect cube, and so you leave your answer just like that. Technically, these negatives would end up canceling eventually, but as far as you're concerned, you cannot distribute this negative in, you can't take this negative out, and so you're going to leave both negatives in your final answer and type it just like that. And so your max is going to be negative CBRT negative 2. Okay, and that is a positive number. It's just hard to tell. Okay. And then for the minimum, let's circle it. Maybe write it over. Just write it down here. So this time we're plugging in the 8, which gives me negative cube root of 1/2 parenthesis 8 minus 4 is positive 4. So negative cube root of positive 2 for this one. 2 is not a perfect cube, so we're going to leave our answer just like that. And so for our minimum, negative cube root of positive 2. Okay, so if you were just looking at these, it's really hard to tell that this red number is actually bigger than this blue number. If you typed them in your calculator and saw the decimals, you would see that this one's negative and this one's positive, and you can tell from the graph. But that's why you need the picture. And that's as ugly as it gets. So if you can handle these, you can handle anything. Oh, I forgot the last one. Ooh. Last one. Being able to write an equation given the transformation. So write an equation for g of x if g of x is formed by reflecting our cube root parent function across the y-axis, horizontally compressing by 1/2, and then shifting left 3 up 11. Okay, so we've got an ry. I like to see it written out. HC 1/2, left 3 up 11. Okay, so they put the g of x equals for us, and so we just need the cube root. Ry means the negative is inside. HC 1/2 means there's a 2. Good form always. Plus 3 for the left 3. Make sure my radical covers that. And then plus 11 outside of all of that for the up 11. So on Canvas, CBRT parenthesis negative 2 parenthesis x plus 3 close parenthesis plus 11 with no spaces. And that's it.